Over the course of human existence, the most significant catalyst for growth has been our ability to draw energy from our world. Taming fire gave birth to the modern human, and drawing power from the wind allowed early explorers to travel the world. But today, we're going to explore the history and science behind one of humanity's greatest inventions, the steam engine. The evolution of the steam engine completely revolutionized our society. It opened new avenues for trade and caused mass migrations of rural populations into the newly industrialized cities. What I found most fascinating was the lessons its evolution taught us about science and engineering. This is one of the first practical steam engines, and it was used to pump water. The engine was incredibly inefficient. This machine was not going to start any industrial revolution, but it found a niche in coal mining, where its fuel was cheap and readily available. To investigate why this engine was so inefficient, let's first talk about how it works. The engine takes energy stored in coal and converts it to heat. That heat is used to form steam, which expands into a piston cylinder, causing the pressure to increase and forcing the piston to rise against atmospheric pressure. No mechanical work occurs on the stroke because this chain can only transmit force in tension. The power stroke occurs when cold water is sprayed into the cylinder. This lowers the temperature, causing the pressure to drop. Atmospheric pressure now pushes the piston back down. We want to be able to quantify how much work is being done per cycle of this engine. To do that, we plot the pressure and volume inside the piston cylinder for one cycle, like this. The area inside is the work done, but this is the idealized PV diagram. In practice, there is a lot more energy being wasted. We lose a big chunk here because the steam is prevented from expanding to its full volume. A lot of energy is lost to the environment too. This is clearly visible with thermal imaging. The effect is made worse by cooling the entire cylinder with cold water. So an immediate improvement is to make a separate condenser. Here the steam can be cooled without cooling the entire cylinder. There are a lot more inefficiencies involved that reduce the total work done. Many of them are unavoidable, but we can improve the situation by upgrading the piston cylinder. The manufacturing techniques needed to bore accurate and strong piston cylinders were not available in the early days of the steam engine. That changed when John Wilkinson invented this machine. This boring machine allowed for precise machining of solid iron cylinders, which reduced steam leakage and made the piston cylinder stronger, thus allowing the max pressure to rise. We are starting to see a steam engine capable of sparking an industrial revolution. But this reciprocating motion isn't much use for most applications, especially with this flexible chain connecting them. What we need is rotational motion, which requires a different setup. To convert this linear motion to rotational motion, we need a crankshaft and connecting rod. We have turned this piston cylinder on its side, so atmospheric pressure can no longer force the piston back down, so we need to use steam on the return stroke. This requires a control valve to control when the steam enters and leaves each side of the cylinder. The valve is controlled by a cam. The steam engine is now working on both strokes of the engine, improving its efficiency and power. But piston engines like this do not produce constant torque. They'll pulsate in speed and torque during a single cycle, like this. This can cause vibrations and jerky movement. We can reduce this with the use of a flywheel, which stores rotational energy with inertia and evens the torque out. It's essentially a mechanical battery. David Robert demonstrates this beautifully with the V8 solenoid engine of his own creation. Here you can see the engine will continue to rotate without additional power, but the engine comes to a dead stop without a flywheel attached. The development of steam engines taught us a lot about thermal and mechanical efficiencies, and you may think that steam engines have become obsolete, but nearly all of our large power stations still use steam technology to convert heat energy, whether that be from coal, nuclear or solar, to mechanical energy. The technology has simply evolved into an even more efficient form, with steam turbines. Thanks for watching. I have one last device I want to include in the development of steam engines, which is one of the most iconic inventions of the Industrial Revolution, the centrifugal governor. I'm already hearing the angry screams in the comment section about me using the word centrifugal, so I'm going to talk about this device in a completely separate video to discuss the differences between centripetal and centrifugal force. If you'd like to see that, don't forget to subscribe. If you'd like to see more content or support Real Engineering, the links for my Patreon, Instagram, Facebook and Twitter accounts are below.